Tell me about yourself.
I recently graduated with a degree in computer science from Central University, where I developed a strong foundation in software development, algorithms, and problem solving. During my academic journey, I worked on several projects, including a task management application that helped users organize their daily tasks and deadlines efficiently. This project allowed me to apply theoretical knowledge to real-world challenges, as I designed the backend using Node.js and Express, integrated a MongoDB database, and contributed to the front-end development using React to create a responsive and user-friendly interface. I am passionate about building efficient and scalable solutions, and I thrive in collaborative environments where I can contribute to innovative ideas. Outside of work, I enjoy exploring new technologies, contributing to open-source projects, and continuously improving my skill set to stay ahead in this ever-evolving field.
What programming languages are you most comfortable with?
I am most comfortable with Python, Java, and JavaScript, as these were the primary languages I used during my academic projects and internships. Python has been my go-to for data analysis and back-end development due to its simplicity and versatility. Java has helped me understand object-oriented programming principles, and I've used it extensively for building robust applications. JavaScript, along with frameworks like React, has been instrumental in my front-end development experience. While these are my strongest languages, I am always eager to learn and adapt to new languages or tools as required by the project or team.
How do you stay updated with the latest trends and technologies in software development?
Staying updated in the fast-paced world of software development is a priority for me. I regularly follow industry-leading blogs, such as Medium, Dev.to, and Stack Overflow, to learn about emerging technologies and best practices. I also subscribe to newsletters like Hacker News and attend webinars or online conferences hosted by tech communities. Additionally, I participate in coding challenges on platforms like LeetCode and contribute to open-source projects on GitHub, which exposes me to diverse coding styles and innovative solutions. Engaging with these resources not only keeps me informed but also helps me continuously refine my skills and stay competitive in the field.
What is software engineering?
Software engineering is a disciplined and systematic approach to the design, development, testing, deployment, and maintenance of software systems. It involves applying engineering principles, methodologies, and best practices to create high-quality, reliable, and scalable software solutions that meet user requirements. Software engineering encompasses not only coding but also project management, requirement analysis, system design, and collaboration with stakeholders to ensure the final product is efficient, maintainable, and aligned with business goals. It is a field that balances technical expertise with problem-solving and creativity to deliver solutions that address real-world challenges.
What are the important categories of software?
Software can be broadly categorized into three main types: system software, application software, and embedded software. System software includes operating systems, device drivers, and utility programs that manage hardware resources and provide a platform for other software to run. Application software refers to programs designed to perform specific tasks for end users, such as word processors, web browsers, or mobile apps. Embedded software is specialized software integrated into hardware devices, like those found in automotive systems, medical devices, or IoT devices. Each category serves a distinct purpose and plays a critical role in enabling modern technology to function effectively.
What is the main difference between a computer program and computer software?
A computer program is a single set of instructions written in a programming language to perform a specific task or solve a particular problem. It is a component of software. On the other hand, computer software is a broader term that refers to a collection of programs, along with associated documentation, libraries, and data, that work together to provide comprehensive functionality. While a program is a standalone entity, software represents a complete system that may include multiple programs, user interfaces, and dependencies to deliver a full-fledged solution.
What is software reengineering?
Software reengineering is the process of analyzing, restructuring, and modifying existing software systems to improve their quality, performance, maintainability, or adaptability to new requirements. It involves understanding the current system, identifying areas for improvement, and applying modern techniques or technologies to enhance the software without changing its core functionality. Re-engineering is often undertaken to address technical debt, migrate legacy systems to newer platforms, or optimize software for better scalability and efficiency. It is a cost-effective alternative to building a system from scratch while ensuring the software remains relevant and functional.
Explain the difference between procedural and object-oriented programming.
Procedural programming is a paradigm that focuses on writing procedures or functions that operate on data. It follows a linear, step-by-step approach, where the program is divided into a series of tasks or routines. Data and functions are treated as separate entities, which can sometimes lead to challenges in managing complexity as the program grows. In contrast, object-oriented programming, OOP, organizes software design around objects, which are instances of classes that encapsulate both data and the methods that operate on that data. OOP emphasizes concepts like inheritance, polymorphism, encapsulation, and abstraction, making it easier to model real-world scenarios, promote code reuse, and manage large-scale systems more effectively.
Describe the difference between interface-oriented, object-oriented, and aspect-oriented programming.
Interface-oriented programming focuses on defining contracts or interfaces that specify the methods a class must implement, without dictating how those methods should be implemented. It promotes loose coupling and flexibility, allowing different classes to adhere to the same interface while providing their own unique implementations. Object-oriented programming, OOP, as mentioned earlier, revolves around objects and classes, emphasizing encapsulation, inheritance, and polymorphism to model real-world entities and relationships. Aspect-oriented programming, AOP, on the other hand, addresses cross-cutting concerns, functionality that spans multiple parts of a system, such as logging, security, or transaction management. AOP allows developers to modularize these concerns into separate units called aspects, which can be applied across the code base without cluttering the core logic. Each paradigm has its strengths and is suited to different types of problems, with OOP being the most widely used for general-purpose software development.
What is the significance of RESTful web services?
RESTful web services are significant because they provide a standardized, lightweight, and scalable approach to building web-based APIs that enable communication between different systems over the Internet. REST, which stands for Representational State Transfer, relies on HTTP protocols and uses standard methods like GET, POST, PUT, and DELETE to perform operations on resources. Its stateless nature ensures that each request from a client to a server contains all the information needed to process the request, making it highly scalable and easy to integrate with various platforms. RESTful services are widely adopted due to their simplicity, flexibility, and ability to support multiple data formats, such as JSON and XML, making them ideal for modern web and mobile applications.
What is the difference between API and SDK?
An API, or Application Programming Interface, is a set of rules, protocols, and tools that allow different software applications to communicate with each other. It defines the methods and data formats that developers can use to interact with a specific software component or service. On the other hand, an SDK, or Software Development Kit, is a comprehensive collection of tools, libraries, documentation, and sample code that helps developers build applications for a specific platform, framework, or technology. While an API is primarily focused on enabling communication, an SDK provides a complete toolkit to simplify and accelerate the development process, often including APIs as part of its offerings.
Explain the concept of multithreading and its benefits.
Multithreading is a programming concept that allows multiple threads to run concurrently within a single process. A thread is the smallest unit of execution within a program, and multithreading enables a program to perform multiple tasks simultaneously, improving efficiency and performance. The primary benefit of multithreading is enhanced responsiveness, as it allows applications to handle multiple operations at once, such as processing user input while performing background tasks. It also improves resource utilization by enabling better CPU usage and reducing idle time. However, multithreading requires careful management to avoid issues like race conditions and deadlocks, which can arise when multiple threads access shared resources concurrently.
What is the difference between stack and queue?
A stack and a queue are both linear data structures, but they differ in how elements are added and removed. A stack follows the last in first out, LIFO, principle, meaning the last element added to the stack is the first one to be removed. This is similar to a stack of plates, where you can only take the top plate. In contrast, a queue follows the first in first out, FIFO, principle, where the first element added is the first one to be removed, much like a line of people waiting for a service. Stacks are commonly used in scenarios like function call management and undo operations, while queues are ideal for task scheduling, buffering, and handling requests in sequential order.
Describe the OSI model and its different layers.
The OSI, Open Systems Interconnection, model is a conceptual framework used to standardize and understand how different networking protocols interact and communicate across a network. It consists of 7 layers, each with a specific function. The physical layer, Layer 1, deals with the transmission and reception of raw bit streams over a physical medium, such as cables or wireless signals. The data link layer, Layer 2, ensures reliable data transfer between nodes on the same network and handles error detection and correction. The network layer, Layer 3, manages device addressing, routing, and packet forwarding between different networks. The transport layer, Layer 4, ensures end-to-end communication, error recovery, and flow control. The session layer, Layer 5, establishes, manages, and terminates connections between applications. The presentation layer, Layer 6, translates data into a format that the application layer can understand, handling encryption and compression. Finally, the application layer, Layer 7, provides network services directly to end-user applications, such as web browsers or email clients. Each layer builds on the services provided by the layer below it, creating a structured and modular approach to network communication.
What are the phases of the software development lifecycle, SDLC?
The Software Development Lifecycle, SDLC, is a structured process that outlines the stages involved in developing high-quality software. It typically begins with the requirement analysis phase, where stakeholders' needs are gathered and documented to define the project's scope and objectives. This is followed by the design phase, where system architecture, data models, and user interfaces are planned. The implementation phase involves actual coding and development of the software based on the design specifications. Once the software is built, it moves to the testing phase, where it is rigorously evaluated to identify and fix bugs or issues. After testing, the software enters the deployment phase, where it is released to users. Finally, the maintenance phase ensures the software remains functional, secure, and up-to-date through updates, patches, and enhancements. Each phase is critical to delivering a reliable and efficient software product.
What are some software development models?
Software development models provide frameworks for organizing and managing the SDLC process. The waterfall model is a linear and sequential approach where each phase must be completed before moving to the next, making it suitable for well-defined projects. The Agile model emphasizes iterative development, collaboration, and flexibility, allowing teams to adapt to changing requirements and deliver incremental updates. The spiral model combines iterative development with risk analysis, making it ideal for large and complex projects. The V model extends the waterfall approach by integrating testing phases into each development stage, ensuring quality at every step. The DevOps model focuses on continuous integration and delivery, bridging the gap between development and operations teams to accelerate deployment and improve collaboration. Each model has its strengths and is chosen based on the project's requirements and complexity.
What are some software engineering methodologies?
Software engineering methodologies provide structured approaches to managing the development process. Agile is one of the most popular methodologies, emphasizing iterative progress, customer feedback, and cross-functional teamwork. Scrum, a subset of Agile, organizes work into short cycles called sprints and relies on roles like Scrum Master and Product Owner to guide the team. Kanban is another Agile-based methodology that visualizes workflow using boards and focuses on continuous delivery by limiting work in progress. Extreme Programming, XP, prioritizes coding practices like pair programming, test-driven development, and frequent releases to ensure high-quality software. Waterfall, a traditional methodology, follows a linear and sequential approach, making it suitable for projects with well-defined requirements. Each methodology offers unique benefits and is selected based on the team's needs and project characteristics.
What are some software engineering principles?
Software engineering principles guide developers in creating efficient, maintainable, and scalable software. The dry, don't repeat yourself, principle emphasizes code reusability and reducing redundancy to simplify maintenance. The KISS, keep it simple, stupid, principle advocates for simplicity in design and implementation to avoid unnecessary complexity. The YAGNI, you aren't gonna need it, principle encourages developers to avoid adding functionality until it is actually required, preventing over-engineering. The solid principles, single responsibility, open/closed, Liskov substitution, interface segregation, and dependency inversion, provide guidelines for designing robust and flexible object-oriented systems. Additionally, the principle of separation of concerns promotes modular design by dividing software into distinct components, each handling a specific aspect of functionality. These principles collectively ensure that software is well-structured, maintainable, and adaptable to change.
What are some software engineering best practices?
Software engineering best practices are essential for delivering high-quality software efficiently. Writing clean, readable, and well-documented code is fundamental, as it ensures maintainability and collaboration among team members. Regularly conducting code reviews helps identify issues early and promotes knowledge sharing. Adopting version control systems like Git enables effective collaboration and tracking of changes. Implementing test-driven development, TDD, ensures that code is thoroughly tested and meets requirements before deployment. Following continuous integration and continuous delivery, CI/CD, practices automates testing and deployment, reducing errors and speeding up releases. Prioritizing security by following secure coding practices and conducting regular vulnerability assessments is critical to protecting software from threats. Lastly, fostering a culture of collaboration, communication, and continuous learning within the team enhances productivity and innovation.
What is a feasibility study?
A feasibility study is an essential step in the early stages of a software project, aimed at evaluating whether the project is technically, economically, and operationally viable. It involves analyzing factors such as the project's scope, required resources, potential risks, and expected benefits. The technical feasibility assesses whether the proposed solution can be developed with the available technology and expertise. The economic feasibility evaluates the cost-effectiveness of the project, ensuring that the benefits outweigh the costs. The operational feasibility examines whether the solution aligns with the organization's goals and can be integrated into existing workflows. Additionally, legal and scheduling feasibility may also be considered to ensure compliance with regulations and timely delivery. The outcome of a feasibility study helps stakeholders make informed decisions about whether to proceed with the project, modify its scope, or abandon it altogether.
What is modularization?
Modularization is the process of dividing a software system into smaller, independent, and manageable components or modules, each responsible for a specific functionality. This approach promotes separation of concerns, making the system easier to understand, develop, test, and maintain. By breaking down a complex system into modules, developers can focus on individual parts without affecting the entire system, enabling parallel development and reducing the risk of errors. Modularization also enhances reusability, as modules can be reused across different projects or parts of the same project. Additionally, it simplifies debugging and updates, as changes to one module are less likely to impact others. Overall, modularization is a key principle in software design that contributes to scalability, flexibility, and maintainability.
What is meant by software scope?
Software scope defines the boundaries and objectives of a software project, outlining what the system will and will not do. It includes a detailed description of the features, functionalities, and deliverables expected from the software, as well as the constraints, assumptions, and limitations. The scope is typically documented in a Software Requirements Specification, SRS, and serves as a reference point for stakeholders, developers, and testers throughout the project lifecycle. A well-defined scope helps prevent scope creep, which occurs when additional features or requirements are introduced without proper evaluation, potentially leading to delays and budget overruns. Clearly defining the software scope ensures that all parties have a shared understanding of the project's goals and deliverables.
How to find the size of a software product?
The size of a software product can be measured using various metrics, depending on the development context and requirements. One common approach is to measure lines of code, LOC, which counts the number of lines written in the source code. While LOC provides a quantitative measure, it may not always reflect the complexity or functionality of the software. Another approach is to use function points, FP, which quantify the functionality provided to the user based on the system's features, inputs, outputs, and interactions. Function points are independent of programming languages and offer a more accurate representation of software size. Additionally, story points in agile methodologies estimate the effort required to implement user stories, providing a relative measure of size. The choice of metric depends on the project's needs and the level of detail required.
What are function points?
Function points, FP, are a metric used to measure the size and complexity of a software system by quantifying the functionality it provides to the user. They are calculated based on factors such as the number of inputs, outputs, inquiries, internal data structures, and external interfaces. Function points are language independent, making them a versatile tool for comparing software projects across different technologies. They help estimate the effort, cost, and time required for development, as well as assess productivity and quality. Function points are widely used in project planning, benchmarking, and performance analysis, providing a standardized way to evaluate software size and complexity.
How can you measure project execution?
Project execution can be measured using a combination of quantitative and qualitative metrics to assess progress, performance, and adherence to goals. Key performance indicators, KPIs, such as schedule variance and cost variance compare planned versus actual progress to identify deviations. Milestone completion rates track the timely achievement of critical project phases. Resource utilization measures how effectively team members and tools are being used. Defect density and test coverage evaluate the quality of the software being developed. In agile methodologies, velocity measures the amount of work completed in each iteration, providing insights into team productivity. Regular status reports and stakeholder feedback also play a crucial role in assessing project execution. By monitoring these metrics, project managers can identify risks, make informed decisions, and ensure the project stays on track.
Can you describe the process of version control and why it's important?
Version control is a system that manages changes to source code, documents, or other files over time, allowing multiple contributors to collaborate efficiently. It works by tracking every modification made to the files, storing them in a repository, and enabling users to revert to previous versions if needed. Developers can create branches to work on new features or fixes independently, and later merge their changes back into the main code base. Version control systems, such as Git, also provide tools for resolving conflicts when changes overlap. The importance of version control lies in its ability to maintain a history of changes, facilitate collaboration, and ensure code integrity. It allows teams to work simultaneously on different aspects of a project, reduces the risk of losing work, and provides a safety net for experimentation. By enabling traceability and accountability, version control is a cornerstone of modern software development.
Give me differences between tags and branches.
Tags and branches are both features of version control systems, but they serve different purposes. A branch is a parallel version of the codebase that allows developers to work on new features, bug fixes, or experiments without affecting the main code. Branches are dynamic and can be updated, merged, or deleted as the project evolves. In contrast, a tag is a static reference to a specific point in the repository's history, often used to mark significant milestones like releases or versions. Tags are immutable, meaning they do not change once created, and they serve as a snapshot of the code at a particular moment. While branches are used for ongoing development, tags are used for marking stable or important states of the project.
What are case tools?
Case, computer-aided software engineering. Tools are software applications that assist developers in various stages of the software development lifecycle. These tools provide automated support for tasks such as requirement analysis, system design, coding, testing, and project management. For example, tools like UML editors help in creating visual models of the system, while code generators automate the creation of boilerplate code. Testing tools streamline the process of identifying and fixing bugs, and project management tools help in tracking progress and resources. Case tools enhance productivity, improve accuracy, and ensure consistency across the development process. By automating repetitive tasks and providing structured frameworks, they enable developers to focus on solving complex problems and delivering high-quality software.
What are some software engineering tools?
Software engineering tools are essential for streamlining development, improving collaboration, and ensuring quality. Version control systems like Git and platforms like GitHub or GitLab facilitate code management and team collaboration. Integrated development environments, IDEs, such as Visual Studio Code, IntelliJ IDEA, and Eclipse provide comprehensive environments for coding, debugging, and testing. Project management tools like Jira, Trello, and Asana help in planning, tracking, and organizing tasks. Testing tools such as Selenium, JUnit, and Postman automate the validation of software functionality and performance. Continuous integration and deployment tools like Jenkins and Circle CI automate the build and deployment process, ensuring faster and more reliable releases. Additionally, documentation tools like Confluence and Swagger help in maintaining clear and up-to-date project documentation. These tools collectively enhance efficiency, collaboration, and quality throughout the software development lifecycle.
What are some software design patterns?
Software design patterns are reusable solutions to common problems that arise during software design. They provide a structured approach to solving recurring challenges, promoting best practices and improving code maintainability. The singleton pattern ensures that a class has only one instance and provides a global point of access to it, which is useful for managing shared resources. The factory pattern abstracts the process of object creation, allowing subclasses to decide which class to instantiate. The observer pattern establishes a one-to-many relationship between objects, enabling automatic updates when one object changes state. The MVC, Model View Controller, pattern separates an application into three interconnected components, promoting modularity and scalability. The decorator pattern allows behavior to be added to individual objects dynamically, without affecting other objects. These patterns, among others, provide proven solutions to design challenges, making software more flexible, scalable, and easier to maintain.
What are some software engineering metrics?
Software engineering metrics are quantitative measures used to assess various aspects of the software development process, product quality, and team performance. Code quality metrics, such as cyclomatic complexity in code coverage, evaluate the maintainability and reliability of the code base. Productivity metrics, like lines of code, LOC, or function points, measure the output of the development team. Defect metrics, including defect density in mean time to failure, MTTF, help identify the stability and reliability of the software. Project management metrics, such as schedule variance and cost variance, track the progress and efficiency of the project against its plan. Agile metrics, like velocity and sprint burn down, provide insights into team performance and iteration progress. These metrics collectively help teams identify areas for improvement, make data-driven decisions, and ensure the delivery of high-quality software within the desired timeframe and budget.
What are some software engineering standards?
Software engineering standards are established guidelines and best practices that ensure consistency, quality, and interoperability in software development. The ISO/IEC 12207 standard provides a framework for software lifecycle processes, covering activities from conception to retirement. The IEEE 830 standard outlines the structure and content of software requirement specifications, SRS, ensuring clarity and completeness in documenting requirements. The ISO/IEC 9126 standard defines a model for software quality, focusing on characteristics like functionality, reliability, usability, and maintainability. The CMMI, Capability Maturity Model Integration, framework helps organizations improve their development processes by assessing and enhancing their maturity levels. Additionally, coding standards, such as those defined by PEP 8 for Python or Google's Java Style Guide, promote consistency and readability in code. Adhering to these standards ensures that software is developed systematically, meets quality benchmarks, and aligns with industry best practices.
How do you handle debugging in your code?
Debugging is an integral part of the development process, and I approach it systematically to identify and resolve issues efficiently. When I encounter a bug, I start by reproducing the problem to understand its behavior and context. I then use logging statements or debugging tools, such as breakpoints in an IDE, to trace the code execution and pinpoint the source of the issue. Once the root cause is identified, I analyze the logic and data flow to determine the appropriate fix. After implementing the solution, I thoroughly test the code to ensure the bug is resolved and no new issues are introduced. Additionally, I document the problem and the fix to help prevent similar issues in the future. This structured approach ensures that debugging is both effective and efficient, minimizing disruptions to the development process.
In the software development process, what is the meaning of debugging?
Debugging in the software development process refers to the systematic identification, analysis, and resolution of defects or errors in the code. It is a critical step that ensures the software functions as intended and meets the specified requirements. Debugging involves locating the source of the problem, understanding its cause, and implementing a fix to eliminate the issue. This process often requires a combination of tools, such as debuggers and logging frameworks, as well as analytical skills to trace and interpret code behavior. Debugging is not just about fixing errors but also about improving the overall quality and reliability of the software by preventing future issues through careful analysis and testing.
How do you test and debug your software system?
Testing and debugging are essential steps in ensuring the quality and reliability of a software system. I begin with unit testing, where individual components or functions are tested in isolation to verify their correctness. This is followed by integration testing, where I check how different modules interact with each other to ensure they work together as expected. For system testing, I validate the entire system against the specified requirements to ensure it meets the desired functionality. During these testing phases, I use debugging tools and techniques to identify and resolve any issues that arise. For example, I use breakpoints and step-through execution in an IDE to trace the flow of the program and inspect variable values. Additionally, I employ logging to capture runtime information, which helps in diagnosing problems that are not easily reproducible. After fixing the issues, I retest the system to confirm that the defects are resolved and no new issues have been introduced. This comprehensive approach ensures that the software is robust, reliable, and ready for deployment.
Describe a challenging problem you faced in a previous project and how you resolved it.
In a previous project, I encountered a challenging issue where the application was experiencing intermittent performance degradation under heavy load. The problem was difficult to reproduce, making it hard to diagnose. I started by analyzing the system logs and monitoring resource usage to identify patterns or anomalies. I discovered that the issue was related to a memory leak in one of the third-party libraries we were using. To confirm this, I used profiling tools to track memory allocation and deallocation over time. Once the root cause was identified, I researched and found an updated version of the library that addressed the memory leak issue. After upgrading the library, I conducted extensive load testing to ensure the problem was resolved and the system could handle the expected workload. This experience taught me the importance of thorough analysis, the use of appropriate tools, and the value of staying updated with third-party dependencies to maintain system stability.
Which process model removes defects before software gets into trouble?
The cleanroom software engineering process model is specifically designed to remove defects early in the development process, preventing them from causing issues later. This model emphasizes rigorous specification, formal verification, and statistical testing to ensure high-quality software. Development teams using the cleanroom approach focus on defect prevention rather than defect detection, employing techniques like incremental development and mathematical proofs to verify the correctness of the code before it is executed. By adhering to strict quality standards and minimizing the introduction of defects, the cleanroom process model aims to deliver software that is reliable and free from critical errors, reducing the need for extensive debugging and rework.
What is quality assurance versus quality control?
Quality assurance, QA, and quality control, QC, are two essential components of the software quality management process, but they serve different purposes. Quality assurance is a proactive process focused on preventing defects by ensuring that the development process adheres to defined standards and methodologies. It involves activities like process audits, training, and creating documentation to establish a framework for delivering high-quality software. On the other hand, quality control is a reactive process that identifies and fixes defects in the final product. It involves activities like testing, code reviews, and inspections to ensure the software meets the specified requirements. While QA is about building quality into the process, QC is about verifying the quality of the output. Both are critical to delivering reliable and high-performing software.
What is strong typing and weak typing? Which is preferred? Why?
Strong typing and weak typing refer to how strictly a programming language enforces type rules. In a strongly typed language, such as Java or C#, variables must be explicitly declared with a specific data type and type checking is enforced at compile time or runtime. This prevents operations between incompatible types and reduces the likelihood of type-related errors. In contrast, weakly typed languages, such as JavaScript or PHP, allow more flexibility by implicitly converting types or performing operations without strict type enforcement. Strong typing is generally preferred in large-scale or complex systems because it enhances code reliability, readability, and maintainability by catching errors early and making the code more predictable. Weak typing, while more flexible, can lead to runtime errors and make debugging more challenging. The choice between the two depends on the project requirements and the trade-offs between flexibility and safety.
What type of data is passed via HTTP headers?
HTTP headers are used to pass metadata between the client and server during an HTTP request or response. They contain information such as the content type, e.g., content type, application/JSON, authentication tokens, e.g., authorization, bearer token, caching directives, e.g., cache control, no cache, and cookies, e.g., cookie, name equals value. Headers can also include details about the client, e.g., user agent, server, e.g., server, and the connection, e.g., connection, keep alive. They play a crucial role in controlling how requests and responses are processed, enabling features like content negotiation, security, and session management. HTTP headers are essential for the proper functioning of web applications and APIs.
When do you use polymorphism?
Polymorphism is used in object-oriented programming to allow objects of different classes to be treated as objects of a common superclass. It is particularly useful when you want to write flexible and reusable code that can work with multiple types of objects. For example, if you have a method that processes shapes, you can use polymorphism to handle different types of shapes, e.g., circles, squares, triangles, without needing to write separate methods for each type. This is achieved through inheritance and method overriding, where subclasses provide their own implementation of a method defined in the superclass. Polymorphism simplifies code maintenance, enhances scalability, and promotes the principle of write once, use many times.
Where is a protected class-level variable available?
A protected class-level variable is accessible within the class where it is defined, as well as in any subclasses that inherit from that class. This level of access control is more restrictive than public variables, which are accessible from anywhere, but less restrictive than private variables, which are only accessible within the defining class. Protected variables are useful when you want to encapsulate data within a class hierarchy while still allowing subclasses to access and modify the data. For example, in a class representing a vehicle, a protected variable like engine type could be accessed by subclasses like car or truck to customize their behavior while keeping the variable hidden from external code. This approach balances flexibility and encapsulation in object-oriented design.
Is it possible to execute multiple catch blocks for a single try statement?
Yes, it is possible to execute multiple catch blocks for a single try statement, but only one catch block will be executed based on the type of exception thrown. In languages like Java or C#, you can define multiple catch blocks to handle different types of exceptions that may occur within the try block. The catch blocks are evaluated in the order they are written, and the first catch block that matches the exception type is executed. This allows you to handle specific exceptions differently, providing more precise error handling and recovery. For example, you might catch a file not found exception to handle missing files differently from a general I/O exception. However, it is important to order catch blocks from the most specific to the least specific exception type to ensure the correct handler is executed.
When do you need to declare a class as abstract?
A class should be declared as abstract when it serves as a base class for other classes but is not intended to be instantiated on its own. Abstract classes are used to define a common structure or behavior that subclasses can inherit and implement. They often include abstract methods, which are declared but not implemented, requiring subclasses to provide the specific implementation. Abstract classes are useful when you want to enforce a contract or blueprint for derived classes while allowing flexibility in how the details are implemented. For example, in a system with different types of vehicles, an abstract vehicle class might define methods like start and stop, leaving the implementation to subclasses like car or bike.
What is the main difference between a stub and a mock?
The main difference between a stub and a mock lies in their purpose and behavior during testing. A stub is a simplified implementation of a component or dependency that provides predefined responses to method calls. It is used to simulate specific behaviors or conditions, such as returning fixed data or triggering specific states, without involving the actual component. A mock, on the other hand, is a more dynamic and interactive object that not only simulates behavior but also verifies interactions between the system under test and the mock. Mocks are used to ensure that certain methods are called with the expected parameters and in the correct order. While stubs are primarily used to isolate the system under test, mocks are used to validate the correctness of interactions and behavior.
What is meant by level zero data flow diagram?
A level zero data flow diagram, DFD, also known as a context diagram, is the highest level representation of a system's data flow. It provides an overview of the entire system, showing how external entities interact with the system and the major processes involved. The level 0 DFD typically consists of a single process node representing the entire system, external entities, such as users or other systems, and data flows between them. It does not delve into the internal details of the system but focuses on the system's boundaries and its interactions with the outside world. This diagram serves as a starting point for creating more detailed DFDs, such as Level 1 or Level 2, which break down the system into smaller, more specific processes and data flows.
How do you work in a team?
Working in a team is a collaborative process that requires effective communication, mutual respect, and a shared commitment to achieving common goals. I believe in actively listening to team members, understanding their perspectives, and contributing my own ideas to foster a productive environment. I prioritize clear and transparent communication, whether it's through regular meetings, updates, or documentation, to ensure everyone is aligned and informed. I also value accountability and take responsibility for my tasks while being open to feedback and constructive criticism. In team settings, I adapt to different roles, whether it's leading a task, supporting a teammate, or resolving conflicts, to ensure the team functions smoothly. By leveraging each member's strengths and maintaining a positive attitude, I strive to contribute to a cohesive and high-performing team.
What are some software engineering projects that you have worked on or are currently working on?
One of the notable projects I worked on during my academic studies was a task management application designed to help users organize their daily tasks and deadlines. I was part of a team of 4, and my role involved designing the backend using Node.js and Express, as well as integrating a MongoDB database to store user data. I also contributed to the front-end development using React, ensuring a responsive and user-friendly interface. Another project I worked on was a library management system, where I implemented features like book search, borrowing, and return functionalities using Java and MySQL. Currently, I am exploring a personal project focused on machine learning, where I am building a recommendation system using Python and TensorFlow to suggest products based on user preferences. These projects have allowed me to apply my technical skills, collaborate with others, and gain hands-on experience in software development.
What are some software engineering challenges?
Software engineering presents a variety of challenges that require both technical expertise and problem-solving skills. One major challenge is managing complexity, as modern software systems often involve intricate architectures, numerous dependencies, and evolving requirements. Ensuring scalability and performance is another common challenge, especially when developing applications that need to handle large volumes of users or data. Maintaining code quality while meeting tight deadlines can be difficult, as it requires balancing speed with adherence to best practices and standards. Integration with third-party systems or legacy software often introduces compatibility and interoperability issues. Additionally, security vulnerabilities pose a significant challenge, as developers must constantly safeguard systems against evolving threats. Finally, team collaboration and communication can be challenging, especially in distributed teams or when working with cross-functional stakeholders. Addressing these challenges requires a combination of technical knowledge, strategic planning, and effective teamwork.
What are some software engineering skills?
Software engineering requires a diverse set of skills to design, develop, and maintain high-quality software systems. Technical proficiency in programming languages like Python, Java, or JavaScript is fundamental, along with knowledge of frameworks and tools relevant to the project. Problem-solving and analytical thinking are essential for breaking down complex problems and designing effective solutions. Understanding of software design principles, such as solid, dry, and KISS, helps in creating maintainable and scalable code. Familiarity with version control systems like Git and collaborative platforms like GitHub is crucial for team-based development. Testing and debugging skills ensure the reliability and functionality of the software. Knowledge of databases and data management is important for handling structured and unstructured data efficiently. Additionally, soft skills like communication, teamwork, and adaptability are vital for collaborating with stakeholders and adapting to changing project requirements. Continuous learning and staying updated with industry trends are also key to thriving in the ever-evolving field of software engineering.